Thanks. Let's begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for these students. Pray you just guide our thoughts today. Help us to use this time wisely, Lord, for your glory. In your name I pray, Lord Jesus. Amen. All right, let me just say a few brief words about the quiz. I will post a solution for it, but just to give you a quick rundown. A, diverge. B, diverge. C, I need your quizzes. Converge. D, converge. E, converge, and you can find the sum. The sum is inverse tangent of 3 minus pi over 2. F, basically E was telescoping. F is geometric. It's kind of funny, but the answer to F, it converges to this. That wasn't something I did on purpose, but it's kind of funny, right? I don't know. Then G, that should converge because you've got like a k to the k downstairs and a k factorial upstairs. K to the k beats k factorial significantly for large k. So you should be able to show that converges by the ratio test, I believe. And H converges basically by direct comparison test. You have that k e to the minus k over 1 plus tangent squared is less than k e to the minus k. The series formed from the sum k equals 1 to infinity of k e to the minus k converges by the integral test if you apply it. So that's pretty much it. Now, like I told you guys yesterday, this material is difficult. If you didn't get some of those, it is not the end of the world. There are a lot of bonus points on this quiz. Hopefully, many of you got a good score on it, even though you missed a bunch of problems on it. We shall see. But I hopefully will have this graded for you this semester. Yeah. Yes, sir.
How much is this quiz for?
10 points. Yep. All right. So I need to prove for you guys today a few things and introduce a few new concepts. I'm going to leave this example up over here because I want to finish it later. It's something I started with the earlier section, but I haven't finished yet. So last time I explained to you this notion of the interval of convergence. I guess before I do anything else, before I erase this, I would like to introduce another concept to you, which is the open interval of convergence. Well, I guess I'll say that again later, but I just erase it and do it again. Never mind. Scratch it. Let's see here. Yeah, we can leave that there for now. All right, so here's the theorem. Let's try to prove it. I'm just trying to prove one theorem today. If we're successful in that, then I will go on and do computation for the most part. Let's see here. So the theorem is as follows. It is in section 12.8, I believe. And this is really the central, in some sense, this theorem says that the domain of power series are boring. Or to quote my son, boring. Let's see here. Okay, so theorem 12.8.2, which is on page 617, says the following. If the sum of a sub k x to the k converges at c, which is not equal to 0, then the power series, let me give this stupid thing a name, S of x, all right. Then S of x converges absolutely for each x with the absolute value of x less than c, the absolute value of c, rather. That's point number one. Point number two, if the series a sub k x to the k diverges at c not equal to 0. Well, let's say it not c, we use a d. At d, then it diverges at all x with x greater than d, f sub I d rather. All right. That is the theorem. Let me draw a picture of it. So here's, here's a number line, let's say. Let's put 0 on the number line somewhere. What this says is that if you have convergence of the series S of x, like right here, right? If this is C, then you're guaranteed absolute convergence. Where? Yeah, you get absolute convergence like this. Now, on the other hand, if you get divergence at, say, D, or you can put it anywhere you want, I'll put it over here. You can put it over here too, whatever. Then what that means is that back to here and over here, like that, I should say included. Well, no, we don't get included. We get possibly at D, possibly at minus. Now we're given that it diverges at D in this second statement. So what it's saying is that if it diverges at D, then it has to diverge everything larger than D, and also everything that's larger than D in magnitude the other direction. So the black is divergence. Now, you're like, well, what happens between C and D if C and D are so arranged? We don't know, right? Don't know. That's no man's land with the given data. It could be convergent, could be divergent. It could be that C is as far out as you can go without getting a point of divergence. Who knows, right? So actually, once you accept this theorem, it immediately follows the thing I told you yesterday, that the interval of convergence has to be an interval. It either has to be the whole reals, which would be the case that you never get a point like D where it diverges, right? Or it can be a closed interval, which is either open, opposed, clopen, like it could be half open, half closed, open, or closed. Those 4 different finite intervals with finite radius of convergence could be one of those cases, right? Or, of course, the other possibility is it's just a singleton, it's just a point. Those results follow immediately from this theorem, right? Do you see that? So if we prove this, then we've proved the conjecture I made yesterday about the structure of the intervals. That's the underlying logic here. So here's the proof. So what do? We see, suppose that the sum a sub k c to the k equals 0 to infinity converges, right? What does that tell us about? Well, thus, by the kth term test, we have that a sub k c to the k does what? Right, this goes to 0 for as k goes to infinity, right? Of course, what else? What other kind of limits are we talking about? As k goes to 5? No, duh. So one of the things you can gather from that is we have that the absolute value of a sub k c to the k is less than or equal to 1 for k for k sufficiently large, right? And we've talked about this kind of logic before. Oh, by the way, the audio is bouncing, right? Okay, good. Does that make sense? I mean, the sequence a sub k times c to the power k, if that's converging to 0, that means the values a k, c to the k are getting closer and closer to 0. You can make them as close to 0 as you want, right? For k sufficiently large, right? So it must follow then that the magnitude of the sequence a sub k, c to the k is less than 1 past some point. If it wasn't, that would contradict the convergence to 0 of the sequence. Yeah.
Just making sure. So saying like for k sufficiently large and like spelling it out, we just do like for k greater than 0.
Oh, yeah. So I have introduced a shorthand, k much greater than 1. Something like that is fine, yeah. Anyway, I won't ask you to prove this, so don't worry. I mean, you guys have got plenty to prove with this stuff. I don't need to test on the proofs of the theorems in this particular. I'm showing you the proof of the theorem so that it's not just a black box for you, so that you have a sense of why it's true. We don't prove just to verify in here. We prove to understand. Okay. Now that may or may not be your way of understanding, but it is a way of understanding. Okay, so now what? Now you can do a direct comparison to geometric. See, because if this is less than 1, that means what? How can let me be careful here. Let me get off the beaten track here. Oh, yeah, I was about to make a well, not a mistake, but all right. So now I want to think about consider the series a sub k x to the k, right? I want to compare that to what? Well, see, he says. Yeah. I'm sorry. I'll get with it here in a second. We have the absolute value of a sub k x to the k, right, is equal to what? It's equal to a sub k c to the k x to the k divided by c to the k, right? That's just an identity. I multiplied and divided by c to the k, right? Why are you going to do that? Well, you're going to do that because you have control. You have control over this first factor, right? And so we can split that off and say that this is equal to a sub k times c to the k, and then absolute value of x to the k, well, x over c to the power k, right? Using properties of the absolute value function. But that is less than or equal to what for k sufficiently large? Yeah, x over c. Oh, sorry, I need to keep my absolute value here. Absolute value of x over c to the k, right? For, I know, take Travis up on his offer to use this notation again. Thank you. Right. Which is just my way of saying it has to happen eventually, and I don't really want to tell you precisely when, and because that would just name a name that doesn't need to be named, and that has to happen, right? Because of the line above. And then we can do direct comparison to the geometric, right? But if we look at the sum of x over c to the, well, absolute value of x over c to the power k equals 0 to infinity just for our convenience, that is what? That's equal to 1 over 1 minus the absolute value of x over c, right? Provided what? We need that the absolute value of x over c is less than 1, which is to say what? Very good. absolute value of x is less than the absolute value of c. Hence, by direct comparison test, we have 1. Right? We've just proved the absolute convergence by direct comparison to the geometric series formed by the quotient of x over c to the power k. Does that make sense? I think it makes sense. Oh, and yet again, the linchpin of a central theorem of this course is the geometric series. It's always the geometric series. It's a conspiracy. It's like the Illuminati, like their first thing. It's geometric series, Trilateral Commission, geometric series. It's all that. All the centralized banks, they all use the geometric series. North Korea, geometric series. See here. Sorry, I digress. Number 2, how do you prove number 2? I won't write anything for number 2. Let's just talk about number 2. What would happen if that series diverged at D? I think we could, right, but I think we could basically follow the same argument, right? If you think about it, like, and what I'm trying to say is if it diverged at D, right, and you suppose that there was some C larger than D for which it actually converged, then that would imply that you have a larger series which converges relative to the series which diverges, right? So you could like do you would violate the comparison test if you basically used part 1 on something that happened to, if you had some other like C out here, let's say C prime, which converged, then if there was a C prime which converged, then it would say that, hey, by part 1, all of this absolutely converges, right? But that would contradict the divergence at the point D. So like 2 is pretty much immediate from 1 if you just think about it, right? If I have divergence at a point D, if I somehow had convergence farther out, then by part 1 I would have convergence all the way in to 0, which contradicts the divergence at D, which we're assuming. That's it. So that's it. That's the theorem. And that's why the interval of convergence is what it is. That's all I'm going to prove for you today. Okay. Now let's do computations, if you don't mind. Yeah? Yes, sir.
I was just wondering,
Oh.
does the C and
For a second, I thought you threw your voice. It was very disconcerting because I was expecting him to talk, but then the voice came from you. It kind of weirded me out. But anyway, go ahead, Daniel. Yeah.
so the C and D, does that mean that they're going to start at the same point? Because if you can find the value of C, does that mean anything outside of C is?
No. If we have let's think about this. Let me get rid of this theorem and let's look at some examples. There's abstract examples, and these are some of my most beloved test questions because they require no calculation whatsoever. They are totally just based on, do you understand the theorem? And to me, understanding of the theorem in this case happens to be more important than your ability to prove it. I mean, that's usually the case in here. I'm more interested in you understanding things and being able to prove them because this is, Calc 2. But you're like, well, you asked me to prove some things. I know it's true. You got me. Okay, so if we have, by the way, there's nothing especially special about 0. That theorem has another version, which is what? I need the other theorem for my examples. The better version of that is if s of x is equal to the sum k equals 0 to infinity, a sub k, x minus x naught to the k, then 1. If s of c converges, then S of x converges absolutely where? You do, let's see here. So the question is, well, let me just write it this way. It converges absolutely on x naught minus delta, comma x naught plus delta, where delta is simply the distance from c to x naught. So it's like c minus x naught. If you unwrap the theorem I just wrote centered at 0, I said that it converged absolutely for absolute value of x less than absolute value of c. That would be the open interval from minus absolute value of c to absolute value of c. So I'm just saying it's like c, absolute value of c was the delta in the theorem I just wrote and erased. But this is what it is. And then 2, if s of d diverged, then s of x diverges. What I'm saying is there's nothing special about 0 in the previous theorem. S of x diverges if x is an element of, say, minus infinity to minus absolute value of d, unioned with absolute value of d to infinity, this ray. This is another way of saying, oh, I still haven't said it right. No, that's not right. It's not right. It's not right. Ah! I got to draw a picture to figure out what I should write here. Here's the picture. Here's my x naught, right? And suppose this is d. I'm thinking about this being the distance delta, right? The point is, the theorem gives us divergence out here, and then distance delta over here. Out there we have divergence out here. That would be, this is like an x could be here, or an x could be here in the divergent case too. What would that be? Like, so x, well, if the distance, see the absolute value of x minus x naught, understand what that is. What is that? I hope you understand that that's the distance from x naught to x, right? That's the distance from x naught to x. So the theorem is saying that if you diverge a distance delta from your center point in the series, then all points beyond distance delta from the center diverge. That's a more geometric way of understanding this. So all I got to do is say x greater than d, okay? Is that right? That's still not right, is it? I want to say greater than delta, right? But what's delta equal to? X naught minus d, right? There we go. All right, let's come on, think about an example here. So if I have like the sum a sub k x minus 3 to the k equals 0 to infinity, converges at x equals to 5, and if I have that it diverges at x equals to 6, what are the possible intervals of convergence for this series? There's a good problem to really test if you understand the concept of the theorem I just wrote. If you understand how to do this problem, then you pretty well understand the theorem I just wrote. So what I do when I'm faced with a problem like this, I draw a number line to organize my thinking. And on the number line, I put one very important thing, which is what? This is a power series centered where? No, not x. C? Yes, C is our notation, or x naught today. I set C equal to x naught relative to the last lecture. Where is it set? Specifically, what? Maybe you said 3 and I heard C. Did you say 3? Yeah. I'm sorry. So 3, yeah. It converges at 5, right? It converges at 5. That's here, let's say. If it converges there, that means that we have absolute convergence. How far is that? That's 2, right? So I go all the way over here to 1. It may or may not converge at 1. I don't know. This particular point, that particular point is the convergence. The convergence or divergence at 1, I can't tell. It's an endpoint. Theorem doesn't tell me anything about that. Weird stuff can happen at endpoints. And then what else do we know? Diverges at 6, right? Now that tells me what? That tells me that if I want to graph where it's divergent, it's divergent all out here. How far is 6 from 3? 3. So over here at 0. And again, at 0, I don't know. It could diverge, it could converge. I'm not sure. Divergence at one point doesn't imply divergence on the other symmetric point on the other side of the center. So at 0, again, it's a questionable point. I don't know. At 0, it may or may not. But definitely for negative values, it's divergent. So then I can ask the question, what's the maximal IOC? What's the maximal interval of convergence is what? One to 5. Nope, could be greater than that. 0 to 6. Now, I would say the greediest thing I can do is 0 included to 6 excluded. That is consistent with the given data, and I can't go past that. Going past that would say that there's a point that is convergent past the divergence point relative to the center is impossible by the theorem. What's the minimal IOC? I hope you don't mind I'm using the word maximal and minimal without defining them. I think you know what I mean by that, right? What's the minimal? What's the smallest IOC that's possible with the given data? Now I think we get what Travis said, which was what? 1 to 5. 1 excluded, 5 included, because that was given to us. That's the smallest interval of convergence that is possible with that given data. And that's how you think about these things. Yeah? Actually, let me tell you something I'm not supposed to tell you, but it's actually worth knowing. The real way to think about these things, honestly, folks, if you want to think about why a certain formula converges or doesn't converge to a given power series, if you just think in terms of real variables, you can't really understand what's going on. So just to kind of, spoiler alert, I'm telling you something in complex analysis here. But I gave you this example before. F of x is equal to 1 over x squared plus 1, or 1 plus x squared, right? And that has, by the geometric series, the expansion k equals 0 to infinity, minus 1 to the k, x to the 2k, right? In other words, 1 plus x squared, but 1 minus x squared, plus x to the 4th, plus dot, 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 dot. Now that was true for the absolute value of x less than 1. And I mentioned to you that is seriously mysterious because, well, there's nothing particularly weird going on with this function. It's just this kind of like bell curve kind of looking thing, right? So why on earth, I ask you, why on earth is it the case that the interval of convergence, right, is just from here to here, right? Why is that the IOC? What's the problem with the formula? Well, here's the thing. The proper way to look at formulas, Gauss would argue, about 200 years ago. For some reason, we still don't think that you should really embrace this. Humanity has yet to embrace this collectively, but we should. is complex analysis is worthwhile. And complex analysis says if you look at this as a complex variable, well, that could be 0, right? This is 0 when you put in x equals to what? Not 1, I. Plus or minus I, you get minus 1 squared plus 1, which is division by 0. So the way we should really think about this is as a complex function. And in the complex domain, if you look at this as the imaginary axis, and if this is the real axis, then you have this actual disk of convergence. It's still true if you think of x as being a complex variable, that you have that series expansion. But now it makes sense why you can't go past modulus 1, because that's where you run into the poles, the singularities of the 1 over x squared plus 1 function. And the radius of convergence is an honest-to-goodness radius, because you have disks of convergence. You have disks of convergence in the complex domain. There are places in real analysis, and especially differential equations, where you have to think this way in order to properly understand how far the solution to a differential equation will extend, because you'll get solutions work up till like a certain point, and that's based on where it actually, if you were to extend the function to a complex function, where it hits the complex singularity. So we actually have to think about drawing complex planes and stuff to understand properly where domains are coming from. So we can understand why that has a problem at plus or minus 1 if we extend it to a complex function and think about disks of convergence. But now I'm telling you things I'm not supposed to tell you, so I'll shut up. Yeah. But we should tell you these things, I think. Otherwise, I wouldn't. I mean, it's not an accident. I told you. I mean, that's the reason I asked the question the other day, so you'd think about it. Anybody have this idea before I told you? No? Okay. All right, so let me see how much playtime we have left. I'm going to have to move the test from Tuesday. Tuesday is too early for this test. I'm not sure if it's going to be Thursday or the Tuesday after yet. I'll have to think about that. But the test is definitely pushed back from Tuesday. Tuesday's too soon. We've gotten a little bit behind. I've tried to catch up, but have not been entirely successful. All right, I'm going to try to stop talking now about intervals of convergence. I'm trying to shift our gears back, talk about how to calculate with power series, how to multiply, how to differentiate, all that stuff, all right? My first point to you is there's an evil homework that I assigned you, I think, where I think he told you to calculate the first 5 terms in the Taylor series. Well, this is bad advice. This is really bad advice, because the way you should do that problem, I mean, you got good practice differentiation. Very good, congratulations. But this is a better way to do it, because this is lazier. So if I'm going to find the Maclaurin series for x times cosine of x squared, I'm going to use substitution and thinking. I'm going to take the known Maclaurin series for cosine. I'm going to replace x with x squared. And then I'm going to multiply x times the series, like this. See that? How do you multiply x into a series? Well, that's kind of easy. It's just that, right? You just multiply like you'd expect. 4k goes to 4k plus 1. And there you go. That's not just the first 5 terms, all the terms. Not so much as a differentiation, right? Pretty sweet. Here is a next level obfuscation of that example. Find the power series expansion for x times sine of x at x not equals to 3. My goal is to write it as something like that, basically, right? Like a particular coefficients times x minus 3 to powers. This is less pleasant. So I look at it and go, okay, well, what this really is, I can add 0, right? And I can create centers at 3. First of all, I take one look at this and I decide, I'm not differentiating this and looking for a pattern. I don't want to. I don't like to. It would take me, like that fourplicity example we did the other day, even that with being somewhat simple was kind of a drag, right? I want to think of a more intelligent way to do this calculation. So what I'm going to do is I'm going to center it at 0 using algebra, and then I'm going to use trigonometry. So trigonometry basically allows me to take the green underlined sine of x, right? I'll call it g of x just for the sake of discussion. And what I can do is use the adding angles formula, right? We did this the other day, right? Is adding angles formula, you get this and that. You got your cosine, you got your sine of 3, multiplying it, right? We did this the other day. What we didn't have the other day was the x in front. This is a new wrinkle in the example. Now, so then what I do is I actually multiply my g of x expansion, right? My sine x, times this thing. So I've got two terms. I've got x minus 3 times sine x, and then I've got 3 times sine x, right? So, so x minus 3 times sine x is just this, right? I've got cosine of 3, these terms. Notice what happens, x to the 2k plus 1, instead x to the 2k plus 2, because I'm multiplying by x minus 3. Over here, I have x to the 2k plus 1, because again, I'm multiplying by x minus 3. That's the terms, these are the purple terms. Okay. Then, I have to add 3 times the sine of x. That's 3 times this, and I'm missing my 3. Oopsie. That earlier section, I tell you. Well, we were at the end of class, and they had already suffered through other things, so it's understandable. There's a 3 there. Now, that's in some sense an answer, but it's not a good answer yet. To make this a good answer, what do I have to do? I have to collect even and odd terms into just one even series and one odd series. If I can write it as a sum of an even and an odd series, I'm happy with that. That's a legit answer here. So here's a place where we actually have to re-index the sum in order to make our answer, in order to simplify our answer. Let me start out by rewriting here. So what we have is we've got f of x. I'm just going to, the odd powers. What do we have for odd powers? See, the odd powers I don't need to do any more work for except just to collect it. Let me write those first. The odd powers. Sum k equals 0 to infinity. And I'll make some big parentheses here. My odd coefficient, right, is 3 cosine 3, right, times minus 1 to the k, divided by 2k plus 1 factorial. All right? That's just the coefficient from here. See what I'm doing? This one and that one. That's my coefficient from this term. Got that? The other place where we have odd powers is over here. And that gives me sine 3 minus 1 to the k divided by 2k factorial. All right? Parentheses, x minus 3 to the 2k plus 1. Those are all the odd terms in the series expansion, the Taylor series expansion of x sine x centered at 3. Now, there are even terms, right? I'm going to use a j for the other one. J equals 0 to infinity, just for some contrast, all right? And so what I did first was I just changed this from k to j already. So that's easy. I'll just write that one down to start with. That's 3 sine 3 minus 1 to the j divided by 2j parentheses factorial. Did I answer your question about the quiz earlier? You had a question about the quiz. I'm not sure I answered it. Okay, wait, okay. I'm easily distracted. So that's just this term. Now, this one over here, I actually have to do some calculation before I can. This one I can't just add. You can't add apples and oranges, right? If I'm going to add two series, what are the rules for adding series? Right, like the rules for adding, you have to have the same range. Very good. The same format also, right? So I can, if I'm going to add, I can add, say j equals 0 to infinity. You have like a sub k x to the x minus x naught to the, let's say, if you had, I mean, whatever you have up here, let me be much more vague about it. If I have Pac-Man here, and if I have, oh, that's weird. sorry. Pac-Man some function of j. Well, if you're going to write Pac-Man of something, I feel like the functional dependence of Pac-Man is better just, there we go. So if I'm going to illustrate a functional dependence of Pac-Man, let it, Pac-Man eats j and gives you out some number. I mean, it would have to be this kind of pattern. You have the same matching, and also I guess down here I could just say, ghost. I mean, the range of the sum has to match, like you said, and also the format of the sum has to match in order to add things. So this, after I multiplied, wasn't good relative to that, because these have different patterns. See, I can't add those, apples and oranges, you know? So I have to make a substitution here. The substitution I make is 2j is equal to 2k plus 2. In other words, how are k and j? I mean, this means k is equal to what? J minus 1, right? Okay, so we just plug in j minus 1 in the place of k in that formula, and that's the other thing. So plus cosine of 3. All right, k minus 1 to the what? What did I just say? J minus 1 divided by what? 2k, yeah, 2 times j minus 1 plus 1, right? Factorial. I'm not trying to clean it up or anything. I'm just writing it, you know? And that's it. And there you go, folks. That is the full Taylor expansion for x times sine of x centered at 3. That's the fastest way I know to do it, personally. Some of you who are really, really good at differentiation and pattern matching might get to this faster through just rote differentiation. I'm assuming that you're a calculational beast, though. I mean, I think the same person could do what I'm doing faster, so I don't know. You're like, well, that's great. What's the point? I don't know. There are fun questions you can ask that test a person's ability to do this without just testing the full thing. What's a way I could test on this without actually asking you to do the whole thing? How about this? I could ask you, what's the 73rd derivative of this function at 3? If you're very foolish, you'll start differentiating. The point is we know Taylor's theorem, right? So we know the coefficient of the 73rd power is what? It's this. Right, so what I want to do is I want to say the 73rd power at 3 divided by 73 factorial is equal to a sub 73, basically. What is the 73rd coefficient here, though? That's even or odd? Odd, right? In my current notation, that means k equals to, no, not 73, 35, 36, right? 2 times 36 is 72, 72 plus 1 is 73. That would be how I get this coefficient here, right? And so there it is. That is 3 cosine of 3 divided by 73 factorial plus sine of 3 divided by 72 factorial. So the 73rd derivative of this function evaluated at 3, multiplied through by 73 factorial, what do you get? Yeah. But if you think about it, right, You don't have to prove the whole thing to answer that. All you have to do is think about, how can I get things of the 73rd power from multiplying the series expansion for the functions involved? How do you multiply power series? How do you do that? Let me show you my idea, what I just said, for another example, and give me a chance to introduce a new concept. Suppose I have f of x is equal to the sine of x squared times e to the x. That's complicated enough. We'll leave it at that. All right. Calculate the, I don't know, 59th derivative at 0 for f. So the way this works, right, is f of x is equal to, well, it's the sum, right? K equals 0 to infinity, minus 1 to the k. Is it CFA?
Yeah.
Hey, where's the CFA? What's up with that? Why? Oh, the afternoon? Oh, man, they missed out on the... Oh, so tomorrow we're going to have CFARs, huh? Should I spend, like, tomorrow just the whole lecture just, like, adding fractions? What's that? Oh, tomorrow's April Fool's? I once, like the second year I was here, I came to my my chairperson. And I was like, "Yeah, I'm sorry. I won't be here in the fall. I took a position at another place. I'm sorry, telling you so late." And I kept it together. I was really, and then all of a sudden it dawned on him what day it was. He's like, said if it was true, he was going to throttle me. I have no doubt that he could. Our chairperson used to wrestle. Let's see here. Let's see, x squared. So it's to the 2k plus 1. So let me cheat over here. 2. Oh man, it's always about to happen. X to the still sick. All right, 4k. I think I proved that. 4k plus 2. That's the sine series. The e to the x series, well, we know that without anything too fancy. Let's say j equals 0 to infinity. Oh, come on. Whatever. J factorial, x to the j. Okay. So you got to multiply these in order to find the power series for that function, right? So what that looks like, I mean, to be more explicit, this is what? This is x squared minus 1/6 x to the what? 6, right? 1 over 5 factorial. X to the, let's see, k equals 2 gives me 10, yeah? And then so forth. And over here, easier, 1 plus x plus 1/2 x squared. How do you multiply series? What's the rules for that? There's a theorem that says that, excuse me, and this isn't the greediest theorem I could state, but it's a theorem that's true. If I have two series, which, let's say that, just for the sake of me not saying something incorrect, you could be greedier, but suppose they have the same interval of convergence, just for discussion. These both have interval of convergence, the whole reals. So when you multiply them, you get another series with the same interval of convergence, and the way you obtain the coefficients for the new series is you just multiply like you multiply like usual, order by order. In other words, you just distribute and collect like powers. So, for example, here, what's the first thing? Well, there's no constant term, right? Because there's no constant term over here to multiply. Is there any linear term? No, because x squared is the lowest thing over here. So the first thing you reach, the only quadratic term, is in fact x squared. Is there any third order term? Yeah. X cubed. That's coming from x squared times x. Fourth order term. Well, yep. 1/2 x to the fourth. Fifth order term. Yep. 1/3 factorial x to the fifth. That's coming from the next thing over here I didn't write yet. Multiplied by the first term over there, right? Fine, let me write these out because they might be helpful for us to visualize what's going on here. All right, so what's the next thing? Now, x squared times x to the fourth. I'm going to do some parentheses here. So I've got like a 1/4 factorial, right? And there's another way I can, but look, I've also got, when I get to the 6th power, something special happens. I've got this times this, but I also have this guy times that guy. They're both leading to this term. You really already know how to do this. You just have to have the courage to do it, right? We're just multiplying like we usually do. What's the next thing? 7th order, I get 1/5 factorial from the x squared times that. And what else do I get? Minus 1/6 from this times this. Is there any other way to get 7? No, so that's it. Now, of course, I don't think I can come up with a clean formula for the kth coefficient of the product, but I can show you a concrete algorithm for how we construct the coefficients in each term, right? So if you wanted to calculate the power series for the product up to, the first 5 non-trivial terms, it's clear enough what you do. You just focus on the lowest order piece of both and you multiply them out and you make sure you keep all the terms possible of each order. What I'm describing right now is called the Cauchy product. All right, so getting back to my insidious question, the 59th power, how can we possibly get a 59th power? Let us count the ways. How can you get a 59? How can you get 59? 59 comes from what? I mean, in principle, it comes from, basically you got 59 times 1, or you've got plus 1 rather, 59 plus 0 rather, or you've got 58 plus 1, or you've got 57 plus 2, or you've got 56 plus 3, or you've got 55 plus what? Am I doing this wrong? No, 55 plus 4, until finally you get to 1 plus 58, or find 0 plus 59. What I'm contrasting here is the order of the left factor versus the order of the right factor. So if you think about this list, right? What can you get in here that gets you something in here? I mean, I guess there's only certain things we can get in this list, right? Yeah, 2 plus 4k plus 2. In other words, yeah. So like there's this. We're starting to see it here, right? We've got the basically, yeah, 2, 6, 10, 14. Oh my goodness, it's still awful. 14. This is all. I'm not going to do that. That is a nasty question. Even that's just not nice. It's not nice. It's not nice. Because I still have to look at all these possibilities. Every one of these has a corresponding, like, if I look at 2, it gets paired with the 57th order term in the exponential. Is there a non-trivial 57th order term in the exponential? Yes. So that happens for every one of these purple things I'm writing, every 4. So you'd have to go 2, 6, 10, 14, 18, 22, 26, 30, 34, 38, 42, 46, 50, 54? I missed something up. I can't do math. Anyway, the point is there's too many. I don't want to do it. Let's do something simpler. The 7th derivative for this one, for example, here. Yeah, the 7th derivative. Now, see, this is just low enough that you might try to do it directly, right? So that over 7 factorial will be equal to 1 over 5 factorial minus 1 over 6. And so you can see that the 7th derivative at 0 is equal to what? 7 factorial over 5 factorial minus 7 factorial over 6. Is that supposed to be 6 factorial? Oh, no, yeah. Okay, so that's 42. It's everywhere. Minus 7, no, but 7 factorial divided by 5 factorial is 42. That's 7 times 5 times 4 times 3 times 2, which is 42 times 1 minus, see there's a 42 in here too if you look for it. See that? These guys are 42 minus 20, so it's 19 times 42. I mean, whatever. It's arithmetic. I mean, you can do it, but. All right, let me give us an example of multiplying series, which is altogether less complicated, okay? How about that? Let's multiply x minus 1/6 x cubed plus 1 over 5 factorial x to the 5th plus dot 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 dot. Multiply that by 1 minus 1/2 x squared plus 1 over 4 factorial x to the 4th plus dot 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 dot. We'll just aim to keep the first, let's say, 3 or 4 non-trivial terms. So let's see, what's the first term? X, all right. What is the next term? Minus 1/2 what? 1/2 x cubed, though, right? But let's say plus, I'm going to put parentheses here, x cubed. I agree there's an x cubed. And I agree that minus 1/2 is part of it, but is that all that there is? Minus 1/6, very good. Is that it? Because it's either this times that or that times that, right? Then we can look for x to the 4th. There is no x to the 4th, though. See, this is odd. This is even. The product of odd and even is odd. The odd powers will all be 0. So the next one, the even powers will all be 0. Good grief. Listen to me. All right, so odd to the 5th. All right.